Hello everyone. Today we have Ioannis to give a talk in the webinar about attosecond coincidence spectroscopy. And Ioannis is a postdoc in our group in University of Freiburg. I'll start with a little bit of history about Ioannis. Ioannis received his undergraduate degree in physics from the University of Vienna. He then pursued a master's degree in photonics at the Friedrich Schiller University, Vienna, before moving to Fort in Crete for his PhD, where he completed his PhD under the supervision of Dimitris Karalimbidis and Paraskevas Salas. His doctoral research focused on the development of high photon flux, HHG-based attosecond source, and its application to study the multiple ionization in noble gases through sequential and direct multiphoton pathways. His postdoctoral work here in Freiburg is focused on the attosecond photoelectron interferometry combined with the coincidence spectroscopy in molecular systems. And he's also involved in a lot of projects in ALU, Fermi, and most recently at Fermi, he was awarded a beam time as the PI, which several of our QU-ATTO members were a part of. And it is my pleasure to hand over the virtual floor. Welcome, Ioannis.
Thank you very much. Thank you very much for everybody for joining for this month's QU-ATTO webinar. So as Suresh told, the title is Attosecond coincidence spectroscopy, and together, Now together we're going to have, let's say, a look into a powerful microscope for electronic dynamics. So I'm going to present you an approach where we combine attosecond photoelectron interferometry with coincidence spectroscopy. So it's a powerful tool that one can use to perform kinematically complete experiments, investigate many-body dynamics and electron-electron correlations. So the seminar is organized as follows. So initially, I will present a brief historical overview with the highlights of the evolution of the apparatus. Then I will introduce the basic principles of the spectrometer. And in the end, in the last, let's say 10 minutes, I will present you some experiments that follow this approach. Okay, but first, let's start to make clear what is coincidence. So coincidence is an experimental technique where we detect multiple particles, electrons and ions, from the same photonization or fragmentation event. So for those who are also working in this field, maybe I have heard also the term covariance, which covariance is a statistical measure, and with this we can extract correlations between two variables without event-by-event tagging. So this has some advantages and disadvantages. The advantage is that one can work in really high repetition rate. Now, when we have a true coincidence, the correlation coefficient will be given by the covariance divided by the sigma of the variable x, and the sigma of the variable y will be different from 0. Today, we're going to look into photoelectron photoion coincidence, which has the acronym of PEPICO, but there are also other ones like ion-ion coincidence, which stands for PIPICO or PEPICO when we have a double ionization, and so on and so forth. Here you can see on the right a coincidence map where we plot here the electron time of flight on the y-axis, and in the x-axis is the ion time of flight. And the one can, let's say, see the islands of true coincidence and the false coincidences. So we're going to tell more in detail later. So let's start with the first measurement of the recoil ion momentum, and was done by Ulrich and Schmidt-Bocking in Frankfurt. For this, they use a static and spatially extended gas targets and room temperature. So those years they were using a projectile beam, as you can see here on the sketch. It was heating the gas which was introduced by gas inlet, and then they could measure the transverse momentum of the recoil ion transverse with respect to the incoming projectile momentum. but they had a limited resolution. And this was limited by the thermal motion. And also they could record only very small solid angle, let's say the order of 3% of the 4 pi. The experiment was to retrieve scattering angles of heavy projectiles in the micro-rad resin. I remember well was uranium-65 plus. So then the next upgrade, which was done, the previous experiment was in 1987, and the next upgrade was in 92, 93, was the introduction of gas jet. So now we have a localized gas target, and by using an electrostatic field, you can see here on the sketch, we have the gas jet. Here is where we are. They applied the electrostatic field is in order of 10 volts per centimeter, and then they were projecting the recoils on the position-sensitive detector. What they also did for the first time here is that they detect in coincidence the projectile and the recoil, and with this they could identify the ionization process. So they could reconstruct the longitudinal recoil momentum with a resolution of 5.5 atomic units. So the purpose of the experiments were to determine the energy gain or loss of the system due to electron transfer. And then in 95, we have the first cold trims measurements. You can see from the first paper. So they were using helium double plus on helium for state selective scattering angle dependent capture cross sections measured by cold target recoil ion momentum spectroscopy. So this is what cold trims stands for. And what they could do is they could get the 3D recoil momentum reconstruction event by event. So you can see on the right a sketch of the apparatus, which starts to remind, let's say, a REMI or a cold trims that we use today. So the first step was to use a supersonic gas expansion. So intrinsically, they had a cold atomic beam, and the gas expands through a nozzle in a micrometer scale, and then forms a well-localized cold beam. And then as a further step, what they did is they pre-cooled the gas reservoir at 14 kelvins, and this allowed them to get improve really the resolution of the longitudinal momentum is 0.13 atomic units. So using a focusing geometry and electrostatic extraction, they also could get a nearly 100% of the 4 pi solid angle detection for low momentum. In 1986, just 1 year after it, we have, let's say, the first REMI. You can see here a high resolution microscope for investigation of dynamics of atomic, molecular, and nuclear reactions. What is this? Is they in the high resolution recoil ion spectrometer, they add a low energy electron analyzer. So as you can see here in the sketch, it's already similar with the REMI that I'm going to show you in more details later. So we have the Helmholtz coils and here the electrodes. So with a combination of electrostatic and solenoid magnetic fields, they could determine the 3 momentum components of one electron. Later on, they had multiple, they could also record more than 1 electron in a later upgrade. And they have also improved the momentum resolution at 0.08 atomic units, and the coincidence efficiency was in the close to 28%. So this, let's say, apparatus opens a variety of experiments that one can do since we detect electrons and ions in coincidence, and one can study, as we said also in the beginning, many body processes, electron correlations, and therefore, let's say, also study state selective reactions. So if you want to delve into more details, I will suggest you to read these really nice reviews regarding the cold trims reaction microscopes. So let's see how the coincidence spectrometer looks like. So this is a sketch for REMI that we have here in Freiburg. So the gas jet is coming from above, originating from a nozzle, intersects with the laser beam, for us is a combination of XUV plus IR, and then ionizes our gas target, and the charged particles will be guided by homogeneous electric and magnetic field onto time and position sensitive detectors. So what we get is we get X, Y, and T per charged particle per ionization event. So the electric field, as we said also before, it comes from the spectrometer electrodes, which are denoted here, and you can also see the Helmholtz coils for the generation of the B field. So the supersonic gas expansion is really important to have a cold target, as we said. So the gas starts from a few bar reservoir pressure. It can be, let's say, 5 bar, it can even go more than 10 bar. And then it expands into a vacuum chamber, let's say 10 to the minus 3 millibar. And what we do then, we select the zone of silence downstream of the nozzle, which allows us to have a collision-free and uniform expansion. So this limits the momentum spread, which is important for the momentum reconstruction. Just to obtain an estimate of the scales, I will also give you some numbers also in, let's say, this section of the seminar. So the nozzle orifice is 30 micrometer, as you can see here, sketch. Then after 4 millimeter, we have a first skimmer. So the skimmer is just to select the beam. The diameter of this 200 micrometer. Then we have a second skimmer, 400 micrometer, and also what we also have in many setups have is razor blades, 13 centimeter after the nozzle, where one can use to truncate even more the atomic beam. Now, in our case, the interaction region is at 30 centimeters, and there the atomic gas beam is, let's say, 2 millimeter. This is an important just to give somebody to estimate what is its interaction region. Okay, because then you need, let's say, how is your beam focused, and then having also the atomic gas beam, then you can get an estimation. Obviously, the atomic gas beam is really, let's say, broader comparing to the laser beam. Now, if we have argon atoms in the Z direction, they will have a temperature, let's say, in the order of 1 Kelvin. A schematic overview of the REMI. Actually, this is the REMI, and this is after we build it. You can see the photo on the right. Now here, what you may identify, this purple line indicates the gas jet direction, and here is where the first skimmer stands, and then is the second skimmer. Somewhere here are the blades, and here is the spectrometer. So the spectrometer, we sketch it, is going to look like this. So the gas is coming through, is denoted here with this green arrow, and then we have the interaction with the laser, and the ion is going to follow a parabolic trajectory under the effect of the electric field and its initial momentum, and then it's going to hit the ion detector. Now, with the blue here, we denote the electrons, and as you see, they're going to follow a helical trajectory because of the magnetic field that we apply. So the acceleration length that we have here is, for the ions, is 30 centimeters, and for the electrons is 10 centimeters, and followed by a drift region, another 10 centimeters, where there is no electric field applied. The electric field can vary. We're going to comment also later how much one, what's the limitations, but to have a feeling, let's say it's 10 or 4, right here, 4 volts per centimeter. And the magnetic field, let's say, is close to 6 Gauss. So again, a sketch of the spectrometer. You can see also a photo here on the right where we're building the spectrometer of the new REMI. And here you can see these are the out coupling boxes, and these are the detectors. So the detectors, let's have a closer look to the detector. The detector purpose is to measure, as we said also before, the impact time and position of its particle. Okay, so remember we need X, Y, T. So how to do it? We start with a multi-channel plate. For example, it's 80 millimeter diameter, and the particle is coming here, is denoted with this arrow, and we use a pair of MCPs in a 7 pair, and then we have an avalanche amplification which can amplify our signal, and we have a gain of 10 to the power of 8. So the total gain after the 2 MCPs. To do so, we need to apply a bias voltage, which is 1.2 kilovolts per MCP. And just to get also an estimation, the pore of MCP pore, if it's, let's say, 10 or 12 micrometer, and the funnel MCP efficiency can go up to 90%. After passing through the MCP, we have an electron cloud, and this is going to hit the delay line wires. So as you can see here on the sketch down right, so the charge is going to hit, and then a signal will start propagating both ends of the wire. And what we measure in the end, we measure the arrival time difference between these two ends. So this arrival time difference is going to help us determine the position along this axis. So if I have two grids, I can reconstruct the X and the Y information. Now, one can think what happens if I have a second hit, and this is quite important, especially if one needs to investigate double ionization. So there is a dead time, and for a square anode, the dead time, let's say in the order of 30 to 60 nanoseconds. And this depends on the signal propagation time. However, the community has, in order to overcome this limitation, what it did is, let's say, one can use a third layer, and then we have a hex anode, which effectively has a 0 dead time. So you can see here a sketch, and we have now the U, V, W, and each pair of these, let's say, places I'm writing allows somebody to reconstruct the XY position. And as we said, this is more suitable for multi-hits that we get in a double, triple, multiple ionization, let's say. Again, some photos, as you see on the left, how a hex anode detector looks like, and we have a square anode detector here. This is from our old REMI when we took it out to change the MCPs. Just a few words about the detector's acceptance. The extraction field, as you can imagine, has to be strong enough in order to project all the ions of interest on the detector. Of course, one wants to have as much more time of flight as possible because this will improve the momentum resolution. However, this is limited by the repetition rate in our case, and our laser system, and hence the generation of attosecond pulse train, it's with a rate of 50 kilohertz. So this is a window of 20 microseconds. Also, since we use a magnetic field to confine our electrons, one also needs to take care of the transversal acceptance in order the electrons, let's say, to not miss the target. So we have the XYT information from the detectors, and I want this information to come to my PC because I want to do the analysis, right? So what we discussed until now is the electron detector, which is this orange box. So the MCP and the delay lines and the ion detector. So when we have the signal from this one, then it will go to a fast amplifier, which will amplify the signal from few millivolts to hundreds of millivolts. And then we're going to go to another module, which is called constant fraction discriminator. Now, for those who are not familiar with this, I want you to remember that even the position information is time difference. So what we measure is always this time. So what we need is a way to determine the arrival time of the of the signals without being dependent on the height and the width of the signal. Because, for example, here in this graph, if I use such a threshold, the determination of the arrival time will not be so precise. So the people what have been developed is, instead of using the threshold, they use just a ratio. And to do so, they take just a fraction of the incoming pulse, they invert it and then delay it in time, and then add it back together. And you can see here that when my signal will cross this line, then I can determine with precision the arrival time. After the CFD, my signal is going to end up to the time to digital converter, which is essentially maybe the most important part of the data acquisition system. Now, just before we wanted just to explain what is this pulsar. The pulsar, for our case, is just a photodiode with triggers by the laser pulse. And as you can see here, when we have a laser shot and an ion hit, then this will allow, let's say, the TDC to trigger. Of course, one can use a different configuration. This I'm just showing one example. So the time to digital converter, just to give you also some numbers from Runtech, and this is also this image from, the bin size is 25 picoseconds, and the readout rate is in the order of 2 megahertz. However, the multiple hits, the time per channel is 5 nanoseconds. So the TDC process 15 time signals if you have X anode, or 11 if you have a square anode. So 6 per X anode and 1 per MCP, and 1 is the trigger. So also a small comment on this one. So as you see here is the trigger pulse, which is coming, and then essentially it opens a group range. So a group range start and group range end. But since I told you that we use the ion will arrive essentially after my electrons. Right? If it has 20 microseconds, my electrons has been already there in the first 100 nanoseconds. So what does it mean? It means that the TDC always records, let's say, the hits into a buffer, and only if I have a valid coincidence, then it's going to register these events. So somehow, let's say, it looks in the past. Okay. So we have the information. So then we can start doing the analysis, but for this we need the reconstruction of the momentum. So we are going to exploit the cylindrical symmetry that the REM spectrometer acquires, and to do so, we express the momentum in the longitudinal part and in the transverse part. I mean, it's pretty straightforward. As you can see, we're going to use only the Lorentz force, and all the rest, it's pretty easy. So we just write down the equations of motion, and then if we consider the electric field along Z and also the B field along Z, what we had is the position. Now I plug into the position the acceleration length, and then I express the electric field as a function of the voltage difference. Okay. In these equations, we don't use a drift length that we saw in a previous sketch, just to simplify, let's say, the equations. And then just if I plug in these numbers and I can solve versus t, then I have the time of light. Obviously, and as somebody expected, the time of flight is proportional to the length and inverse proportional to the voltage difference. And also, it's not a surprise that the time of flight will not depend on the magnetic field. So what I'm interested from this formula essentially is the initial longitudinal momentum, which you can see here written down. And ion time of flight, a typical time of flight is going to look like this. Here we use a mixture of carbon dioxide and argon. So one can identify the single charges, the double charges, some isotopes, some dissociations, and also water that is always present in our chamber. Just a small note is that here you can see that we plot versus mass over Q over charge, which means that certain different species like O plus and the dimer double charge will have identical flight times. The electrons, on the other hand, they're going to look like this, and most of them are going to arrive before 100 nanosecond under the voltages that I told you before. However, might be a surprise why, since I use an attosecond pulse train, I'm not getting the expected, let's say, frequency count. So to do so, I need to apply the momentum conservation. And here I show you the photoelectron spectrum in coincidence to argon plus ions. We also have the impact position. And here you can see on the left the ion detector, and on the right the electron detector. And what you can note also here is that in the ion detector, the distribution is slightly shifted, let's say, in the y-axis. And this happens due to the jet velocity, which is, let's say, towards the y-axis. And we can see here, if we plot the x position as a function of the time of flight, you see that most of my distributions, almost all of them, let's say, are in this line. However, here, if I plot the y, you see that there is a slope. Okay, and one can identify here, for example, this is the CO2, this is the argon, and the more heavy my particle is, the more down will be in this plot. But then also somebody can identify that some distribution is like a blob. And this is because I have dissociation. This is the CO plus and this is the O plus. But I have a blob that is also here, which is not following the slope. And this is because this is water, and the water that is inside the chamber. So by this plot, one can identify which, let's say, particles are coming from the jet and which particles are already inside my chamber. And then we also have this one, which say, okay, what is this so fast? Essentially, this is krypton, which is left in the jet. So probably in the previous measurement, the krypton was left there, and it is really more heavy compared to the CO2. So we will come to the next window. Okay. And you can identify also here that krypton is with its famous isotopes. So let's look now in the transverse momentum. As we said, the electron impact position will depend on the magnetic field, which and the electrons will follow a cyclotron trajectory along the spectrometer axis. Again, we start with the equations of motions. I will not bother with the details. Just let's comment that the position will depend on the initial perpendicular velocity, and this omega c, which stands for the cyclotron frequency. And it's no surprise, it depends on the magnetic field. So we express the distance from the origin to the detector, and here in the sketch, you can see this arrow denotes the initial perpendicular momentum, and then we have this is the cyclotron trajectory, and you can see that at some point, if we pass some time, which is equal to the cyclotron period, it will come to the origin. And if I plot the RE versus the time of flight here on the left, you can see that it goes at 0 at some point. And one also can identify here that the different trajectories correspond to the different harmonics that I have, okay, because I have a harmonic comb. So when the electron impacts at RE equals 0, it's not possible to retrieve the perpendicular velocity components. And when I plot in this figure the transverse momentum versus the longitudinal momentum, then I'm going to get this, as we call, magnetic node. While in the kinetic energy versus angle, the magnetic node, obviously, since I go from momentum to energy, I will have this, let's say, parabola shape. So we also can express the initial transverse momentum, which depends on the cyclotron frequency and the RE. I also have to mention that these measurements are done using, as I said, XUV plus IR ionization in helium atoms. So I need to. I cannot click. Just a small. Okay, so that's a simulation in a sim-ion simulation where you can see here the electrons are traveling towards the detector, and you see the follow, let's say, the cyclotron motion, and at some point the ions were going to travel on the other way. Now, if I rotate my spectrometer, one can identify clearly the cyclotron trajectories of my electrons. Okay, and also at some point the ions will appear. And you see also the electrons, they will pass also, let's say, in the middle of the detector. Okay. Now, as we said, these data are coming when we ionize helium atoms using XUV-IR. So if we go here, then we can identify that the strong distribution, which is denoted with this arrow, are coming from the XUV ionization, which we call harmonic peaks, and the in between there are the so-called sideband peaks. Now helium is 1 square, okay? So if I absorb one photon, I'm going to have in the continuum a P wave. While if I absorb another photon, an IR photon, I'm going to end up in an S wave in the continuum or in the D wave in the continuum. And if we look here, let's say in the PRPZ map, the harmonic distributions, they will not have, let's say, there's no distribution along PZ equal to 0, which indicates that I have a P wave, while especially in the first sideband, I think it's really amazing result that one can identify that here I have a D wave and an S wave. Of course, here for the next sidebands, one needs to really saturate even more the map to see that I have a really small distribution also along the PZ equals 0. So the REMI is a really nice tool for if somebody wants to investigate photoelectron angular distribution, okay, in atoms, but also in molecules, which we're going to discuss also in later. Now, just to somehow, let's say, expand your perspective, I wanted to tell you, I mean, there are more complicated setups that are using reaction microscope. And one of these is when this Fischer et al. And Kurz et al., what they did is they combined a magneto-optical trap with a REMI in order to investigate cold lithium atoms and weakly bound timers. I think these things become slightly complicated, so it's not an easy setup, but just to give you an overview that we can use a REMI also for more complicated investigations. Now, let's continue to the last part of the seminar, where I want to show you some experiments where people combine attosecond photoelectron interferometry with the reaction microscope or collisions. I will not explain a lot about the laser-assisted photoionization and the Rabbit technique because Pascal already introduced it. And if you're not familiar with this, I recommend you to see again the tutorial. And also, as Pascal nicely also said during the tutorial, during the previous webinar. So the sidebands, if we look at the sidebands, let's look at the sidebands here in the box. They will oscillate nicely with 2 omega AR, with where the frequency of the driving field. And then we have a phase offset delta phi, and this is the most interesting part. Now, if we divide this delta phi by 2 omega, what we're going to get is express this phase in time. and I split it in two main parts. The one which is comes from the relative phase of consecutive harmonics is the so-called ALU tube, and the other is the target response. Now, the target response essentially is the argument of the complex two-photon matrix elements, and from this one can relate it to the so-called Wigner time delays, attosecond photonization time delays. Unfortunately, there's no time to go into detail into this, but there will be another seminar, another QU-ATTO webinar given by David Busto, so dedicated to this topic. It will be in 2 months from now. So this attosecond interferometry, in our case, is realized in a collinear configuration, and we use two drill fuse silica plates in order to synchronize the two color field with subcycle precision. And the two fields propagate and then getting focused by a toroidal mirror inside the reaction microscope. Just before I present you results with REMI, I wanted also to tell you that, of course, one is possible to perform coincidence spectroscopy without REMI. And in this experiment here, they were looking into electron-electron coincidence, just using a magnetic bottle, and they were investigating photonization dynamics in xenon 4D and measuring coincidence in electron and photoelectron. Also, I think it's worth to mention, even though it's more, let's say, applicable for covariance analysis, that one can use a double-sided VMI, and instead of the traditional delay line detector, use a Timepeaks camera. So this is a camera which is event-driven mode, and you get, apart from the X, Y, and the intensity, with a normal camera, you can also get the time of arrival information. And then, essentially, you have the XYT, as we said, for the momentum reconstruction. So let's proceed. One of the first experiments, one of the benchmark experiments, combining a Rabbit technique and the REMI. So they were in this work from the Ursula Keller's group. They were investigating orientation-dependent time delays in carbon oxide molecules. So they defined the stereo-Wigner time delay, which is the difference, if let's say, of the time delay from the carbon side minus the time delay from the oxygen side. So when we have a parallel orientation, as you can see here from the figure, the delay, so here the plot the time delays, the delay will reflect the electron localization along molecular axis. And here in the figure, you can see that for low kinetic energy electrons, it's more likely that the electron will escape from the carbon side, while for higher kinetic energy, is more likely to escape from the oxygen side. Also, another experiment looking also into the anisotropy of the molecular potential was done by our group, but the measurements was done in Milano. And then looking into direction-dependent delay differences in CO4, they could see this anisotropy, especially near safe resonances. Another measurement was done in water clusters by the Vernus group, where they were able to identify and measure cluster size dependent time delays. And this was linked to the spatial delocalization of the electron hole created upon photonization. As you can see here, the bigger the cluster, essentially you have a higher relative time delay. Also more recently, from the same group, they were investigating chiral molecules and essentially propylene oxide by using a circularly polarized XUV and changing the helicity of the IR pulse. They will be able to perform enantiomer resolve measurements. As you can see here, there's a time delays between the two enantiomers. So in our lab in Freiburg, first we wanted to investigate what would be the effect of the nuclear dynamics upon photoionization. For this, what we did is we chose two isotopologues, methane and deuteromethane, and by performing essentially the measurement, what we identified is that the different nuclear evolution will manifest itself on the modification of the contrast. As you can see here, the contrast between the CD4 and CH4 is different, while there is no phase difference between the two isotopologues. So same results we got looking in the dissociation products, and this also has been nicely reproduced by the simulations. So essentially the key results here is that even if we have fast nuclear dynamics, in the absence of a safe resonance or another resonance, will not affect the phase of the photoelectron wave packet. Also, as a last experiment, I wanted to show you is what is the role of ion dynamics into the phase of the photoelectron. And for this, what we did is we choose the CO2 as a target. And for CO2, the binding energy between this cationic state, the beta sigma U and the C sigma G, will match the photon energy of the IR. So we perform laser assisted photoionization. So there is going to couple these cationic states, and this will change the way we describe the traditional, let's say, rabbit to pathway rabbit. So due to this ionic coupling, a third path will arise, as here is denoted here in the middle, where the IR will not induce a continuum transition as we usually have in the rabbit, but essentially is what it's going to do is going to project the C cationic state into the B cationic state. So in the end, I'm going to end up to the same quantum state. So this will allow interference to happen. And then I can record this interference with my photoelectron spectrogram. So upon XUV ionization, before the IR, let's say, arrives, one needs to express now the states not as a product states, but one needs to express, let's say, as superposition between the B and the C cationic states. So these three pathways, they're going to interfere, and this will lead to an additional time delay, which we call ion coupling delay. Essentially, it's from here you can see that this is the argument, and these two terms correspond to the, let's say, traditional or standard two-pathway rabbit, while when this term and this term corresponds to the ion coupling delay. Now, this delay in the high energy limit and for a given molecular orientation and specific photoelectron emission direction can be expressed with this formula, where one can identify the detuning and also the transition dipole in the cation, and this is the common polarization direction of XUV and the IR. And also there is another function here, which we call XY, and essentially this function depends on the purity or on the degree of entanglement of the reduced density matrix of the residual ion. So when we have a high degree of entanglement, this goes to 1. So it's, let's say, the ion coupling is maximum. However, when we have a product state, then this goes to 0. So there is no ion coupling. So the observation was not trivial, but somehow we succeed. And so here you can see the experimental data points with the red circles, and I have 3 different theoretical curves. So the green one is just the static exchange theoretical curve, which is not by default able to reproduce this coupling. However, between the black and the black solid curve and the blue dash dot curve, we can switch on and off the BC coupling. So for high kinetic energy photoelectrons, we have a better agreement with the full model when the BC coupling is on. Now, due to the vectorial nature of this coupling, when we reduce the photoelectron emission angle from 0 to 20 degrees, then we have this agreement is really, let's say, improved. Here, the orange corresponds to the model with the BC coupling on, while the blue one corresponds when you switch off this coupling. So the coupling delay essentially will depend on the degree of entanglement of the reduced density matrix of the residual ion subsystem, and if we, let's say, condition it with energy absorbed by the harmonic 2q plus 1. And what will IR do is going by projecting the C to the big ion states, we're going to convert this entanglement into coherence. And this allows us to observe the Rabi oscillations. What we also recently do is we look into the dissociation channel and exploit the fact, which is also a key fact also for the success of the previous measurements, is that since the C cationic state completely dissociates, what we're able to do is by looking into the photoelectrons in coincidence to the O+, we observe here, as you can see, a pronounced jump in phase, which is close to pi shift, which is attributed to the same BC ionic coupling. So obviously there's no time to go into details, and here I give you a list of I think that most of the experiments that follow the same approach. So if you're interested in the topic, I really recommend you, let's say, to go to the initial manuscripts. And with this, I think we're good on time. I would like to thank all the group in Freiburg, all the group members in Freiburg, and also the collaborators that essentially contribute in the works I presented in the last slides. And thank all of you for your attention.
Thank you, Ioannis, for the great talk. Now it's time for the questions. Should I stop recording to encourage questions?
Yeah, if somebody is not on, yeah, maybe somebody is shy, or everybody knows everything, or nobody understood anything.
Carla have a question.
The question is about the delay line. In your sketch that explains how it works, you were showing the event spreading over multiple lines, and so you have 3 peaks.
At least, yeah, in this case, because yeah, you mean the electron cloud essentially it might hit another, not just one wire. What they don't show, maybe you're no better than me. There's not just one wire. Essentially, there are 2 wires. So because the one is used also as a reference. So so every grid has 2 wires. One is the signal level. One is the other is the reference, just to avoid also from background noise. But essentially, your question was different, or?
Well, my question is if in practice you have to process that. Let me see if I can draw on the sketch. Okay. So here, if your signal analysis has to process a single peak, the big envelope, or 3 separate spikes.
I can tell you for sure that in the end, what we get from the outcoupling box will be one Gaussian or something like this. I never saw, let's say, in our signal, let's say, saw 3 separate peaks under a greater, let's say, envelope. What can happen, okay, you can have, let's say, one as a noise really later, but such a thing, okay, this I think is a sketch. I took it from Fechner's PhD thesis. So to answer the question, it's only one pulse that we define.
The other is rather a comment on what you said about the difference between coincidence and covariance. Essentially, coincidence should be able to be handled by the same equations as covariance, because it's a special case of covariance.
Yeah, I agree, yes. I hope I didn't mention something different than this.
No, well, of course, it's when you think the advantage of coincidence is that you are really counting events and you're throwing away everything where there is no coincidence. In covariance, you're trying to do the same, but you're limited by the fact that the repetition rate is higher.
Yes.
But from the statistical point of view, they are exactly the same thing.
Yeah, I agree. What I didn't mention though, and thanks for the opportunity, I mean that in coincidence, for example, that here we have a 50 kilohertz system. The coincidences were going to be safe. We work in the 10% of it. So we work, let's say, in the 5 kilohertz events. So this has, let's say, leads to really long measurements, which needs a really stable, in our case, really stable collinear interferometer, and let's say your experimental conditions need to be really stable. The results I show you are after recording 90 hours, let's say, continuously. Okay, I mean, okay, now in Fermi, okay, Carlo, okay, you have stability, we have better stability, but okay, in the lab with HSG, okay, one needs to pay attention or to try to get it.
What is the actual limit on the duration of an experiment? I suppose you couldn't continue for a week because something would get unstable.
Essentially, that was the measurements that I saw. Now that we moved in the new lab, we could be able to measure with two weeks consecutive. But we also look different processes, and that's why we need more statistics. Because for the results I saw, I think was enough, both in CH4 and CD4, and also in CO2. This was enough to extract some, let's say, valuable data.
I think Diego have a question.
Yes, I have a question. So my question is for the driver lasers, what wavelength did you use? Because you said it was mid-infrared, so or infrared. So what?
Yeah, it's a terbium laser system. In the last 2 experiments, okay, it was a terbium laser system, 1022, okay, somewhere there.
Okay.
The nominal value is 1025.
Okay, and I have another question. Have you thought or investigated just theoretically or with simulations to use a longer wavelength, like 2 microns or 3 microns, something like that?
To achieve, for what purpose, you mean?
No, I mean in the driver laser, just the laser that you guide into the gas jet.
Yeah.
So have you investigated or simulated the idea of using like a 2000 nanometers or 3000 nanometers wavelength, central wavelength, or?
I mean, it's there are laboratories that are using. I mean, they are you mean to drive harmonics, I guess, or?
No. For the thing that you have explained. Yes. At the beginning of the presentation.
Okay. So I mean, the beginning. Oh, what? Oh no, not here. I guess.
Not
Maybe
here. I just saw it.
when we start having the rabbit here or something.
Yes. No. A little bit back.
Back here.
Yes. No,
back
more,
here.
more.
More back.
Yes, more. Back. More.
Yeah.
No.
More.
Let's see. No. More. Here.
Yeah.
Here. No, the next one. No.
This.
Yeah. Okay. So when you use here, that you use a laser beam that you focus on the gas jet. Yeah. So you said that it was an infrared laser, right?
Yes.
Yes. So my question is, have you investigated the idea of using longer wavelengths for that driver?
Okay, I don't really understand the question. It was essentially, so the laser that we use,
yes,
it drives the harmonic generation process. Okay, it comes directly from the terbium system that we have. Now, of course, one can tune his cutoff if, let's say, goes to drive the HG process with a mid-IR laser.
yes,
okay, this comes with a price. This comes with the price of the efficiency. So, in our case, what can also do is to have a tunability in the XUVIR, and people are doing after the generation of the harmonic, have a third path. Let's say is recombined, and then this pass through an OPA, and instead of having the same, let's say, wavelength that drives the HG process, can have, let's say, I don't know, the second harmonic or some tunability. However, this tunability needs to match, because if you want to do rabbit, your harmonic, let's say, gap needs to match, let's say, with the IR, right? And now this can be 2, can be 3, can be 4. People have tried all these approaches. In our case, we have not tried because we don't have this opportunity in this lab. So to change the laser wavelength.
Okay.
It would be interesting, though, in the last experiment to do so, in the sense that the coupling also depends. The IR coupling will depend in the CO2. The ionic coupling will depend on the wavelength. Okay, it's like projection. So if somebody can tune the wavelength, essentially should be able to affect the coupling. And we try this idea, I would say, in helium in Fermi, but where we have excellent tunability. Okay, it was not rabbit; it was a different. I think it's a topic for a different seminar. But we also thought, what if one can tune, let's say, this detune the coupling? What will happen?
Okay. Thank you. That was the question. Thank you.
Thank you very much for the question.
More questions? There is no more questions. Let's thank Ioannis for a nice talk. Thank you, everyone, for being a part of it. And see you next month for the next webinar.
Thank you very much for joining. See you in the next quarter.
Bye-bye.
Webinar.